What's that? An enol? No. So when you're looking at your enols, it always tautomerize back to the carbonyl. So if at best we drew that out, it would go right back to the aldehyde. It's already there. Are all of those valid answers? No. First one's wrong. Second one's wrong. Okay. And since it was then listed, also heard that this should show up as a possible product, carboxylic acid. And also wrong. Sodium borohydride does what? It adds a negative hydrogen. What type of reaction? A nucleophilic addition. Keep going. And I know a bunch of people shouted stuff out. No, I did not hear the correct answer. So we've got an example of it right above, right? Take a ketone down to an alcohol. What type of reaction was that? Yes, that was a nucleophilic addition. Yes, that was an addition. Keep going.
Reduction.
It's a reduction reaction. Why is the carboxylic acid not a possible product? Okay. We could look at that as oxidized. Officially, it's neither. Why is that a neither?
Oh, because you are replacing one electronegative atom.
One electronegative atom with another. So we added a reagent that should do a reduction and didn't do a reduction. Okay, so well, that doesn't make sense. So that carboxylic acid is wrong. That leaves us with only one option, taking it all the way down to the alcohol. Okay, which well, half of your answer choices gave that, so that's not too bad. That's what it did in the first case when we looked at aldehydes and ketones before. Converted a carbonyl into an alcohol. Okay. So we would kind of lean towards those answers. Okay. If we looked at our original or full mechanism, our hydride donates in, we break, we form the what? Intermediate? Our tetrahedral intermediate, which then does what? We kick out our good leaving group. Okay? So instead of just saying, oh, carbonyls become alcohols, we have to be a little bit more careful and look at our intermediates and our structures to understand something about the mechanism. Okay? The result of that is that I would end up with which functional group? An aldehyde. But we also crossed that off the list. Why did we also cross that off the list? Sodium borohydride reacts with aldehydes just as much as it reacts with acyl chlorides. And we get another hydride addition. We would form, again, a tetrahedral intermediate. Okay. Again, those electrons would try to come back down, but what happens? There's no leaving group. So the electrons can't come back down, and it would stall temporarily there until we followed that up or paid attention to our solvent. And we would end up with our final alcohol. Irritatingly drawn like so, because it looks like I got rid of the carbonyl altogether and I did a substitution. The OH for chlorine. It's not really what happened. Okay. Kind of makes sense? Following the pieces? So what other reducing agent is there? Come on. Yeah, we get it. There were two nucleophilic hydride reagents. We had lithium aluminum hydride, sodium borohydride, would you say? Lithium, okay. NaH, and since it was mentioned in office hours, NaH, what's the issue with NaH? It's a base, not a nucleophile. NaH is so reactive that it does not dissolve, and we're looking at a heterogeneous system. NaH is effectively massive, okay, which is kind of weird. Okay, so write it up here just so everybody knows. Sodium hydride, not a good nucleophile. Okay, horrible. Only acts as a base. And when we looked at lithium aluminum hydride and sodium borohydride, did we notice any differences in their reactions? Okay, the lithium aluminum hydride, which we talked about, admittedly kind of stupidly, okay, was more reactive. Okay, lithium aluminum hydride, more reactive. Did that change how it reacted with the species we looked at? What species did we look at?
Sodium borohydride.
What did sodium borohydride and lithium aluminum hydride, what did they get added to? Aldehydes and ketones. And in those reactivities, did we see any differences? No. We could reference the nitrile. I think we looked at the nitrile, and lithium aluminum hydride would react with the nitrile, and sodium borohydride did not. So for the most part, we saw them as the exact same chemistry. Okay? Why are they now making a comeback? What are we looking at now? Acyl chlorides, amides. We're looking at polar pi bonds with leaving groups attached. Okay? Is that going to now potentially elucidate the difference between sodium borohydride and lithium aluminum hydride? Yes. Sodium borohydride, being the weaker hydride reagent, will react at which end of this spectrum? The chloride or the nitrile? Well, actually, I'm just going to erase the nitrile altogether. Okay. The borohydride is a weaker hydride reagent, which means it needs to react with what? The most reactive electrophiles. So it will react with our acyl chloride. It will react with our formaldehyde and aldehyde. It will react with the ketone. Okay? It does start to react with the amine. Okay? What happens as we add in other functionalities, say like the ester? Okay? This was not the image I thought it was coming in. Okay, the ester, or the acid, or the amide. Well, it stops reacting. What happens with lithium aluminum hydride? It reacts with everything. Okay. Since I thought there was a slide on it, maybe I do. Your textbook kind of nicely summarizes this by looking at the polar pi bonds with leaving groups, or carboxylic acid derivatives, and summarizes it all the way down. Sodium borohydride, you notice, will react with the acid chloride and the acid anhydride, the two at the very top of our reactivity scale. It does react with the ester, though you'll notice that they also add a little caveat. What's that caveat? It's very, very, very slow. Why would it react slowly with an ester? There's a resonance stabilization coming from the oxygen, which stabilizes the electrophile. We could try and address something about sterics. So if we look at that steric argument, the ester versus the anhydride, which of those do you think is more sterically hindered? The anhydride is much larger. We would expect it to be more sterically hindered, and yet it reacts faster. So is sterics a valid argument? No, it's an electronic effect, a resonance effect. Okay. Where do aldehydes and ketones fall in this? Our acid chloride was our most reactive, and our amides at the bottom were our least.
Fall between the anhydride and the ester.
Okay. Our aldehyde and our ketone fall in here. Why are they more reactive than the ester? What's that? No resonance. Why are they less reactive than the anhydride? Kind of. I don't quite accept resonance, because if you're saying resonance with the anhydride, okay, so yeah, it has resonance, but the side that's reactive doesn't have resonance. Okay, so a resonance argument at the anhydride level is a bad argument to make. Why are the aldehyde and the ketone lower in reactivity than the anhydride?
More positive carbon electrophile.
Which one's more positive?
Anhydride.
Why is the anhydride more positive? Yes.
Because it's pulling from the resonance portion of it.
I don't accept the
The
resonance.
anhydride, well, the oxygen, hey, if it moves resonance this side, that carbon out there is now more electrophilic.
The resonance is a null effect. If we don't have resonance as an effect, what do we then need to move to? An inductive effect. When we're comparing the anhydride to an aldehyde, what are we comparing? Hydrogen versus oxygen. Inductively, oxygen being more electronegative makes that electrophile more electrophilic. Okay? We're still applying the same rules that we started way back in first semester. Okay? We just have to be a little bit more careful about when and how we use them. When we move over to the acids, notice what happens with the lithium aluminum hydride. It reacts with every single one of them. Okay? And in all of those cases, we produce alcohols, right? No. Okay, why are we not getting an alcohol in that last one? Because what? What's the leaving group? Why is water leaving and not the nitrogen? Why is water a better leaving group than the nitrogen?
The nitrogen will be in charge.
Oops, sorry. We shouldn't actually have water as a leaving group because we're in lithium aluminum hydride. Can't have anything to protonate that. Why would the oxygen leave instead of the nitrogen? H3O is not present, so we can't use H3O+. That's the second step. What were you saying, Tyler?
Oxygen can stabilize the negative charge better than nitrogen can.
Oxygen is a better leaving group than nitrogen because it stabilizes the electrons better. How does it stabilize the electrons better? Not you, Tyler. We go through and evaluate charge. They're both charged. The next thing is size. They have the same size, nitrogen versus oxygen. The next thing is different, electronegativity. Oxygen is a greater electronegativity, which means it's going to stabilize that negative charge better by holding it better than the nitrogen. So we can evaluate and look at those pieces. When we work all the way through our mechanism, we end up seeing that we end up with the amine when we do a reduction of the amide, not the alcohol.
So from this standpoint, is that when you would add the H3O? So then
After it leaves, yes. Then you would add it. Huh?
So we'll end up with a carbocation then? With the OH?
Yes. A resonance stabilized carbocation because of the nitrogen. Then we'd have an imine. What's special about the imine? What do we have there? Classify that structure for me. It is a polar pi bond in the presence of lithium aluminum hydride, which then reduces it again. Whoops. And we would end up there. That is when we would add the acid. Okay. In this case, the acid isn't going to do much, okay, because we had a secondary amine, which I started with a little bit weirdly, but yeah.
Would the acid just neutralize the base in solutions that you have
Yep.
OH leaving?
The acid is primarily there to neutralize all of your base and any negatively charged intermediates. Okay? Kind of neat. So why barely the esters? What is our difference between our ketone aldehyde and acyl chloride, which we've talked about now multiple times? So if I wanted to do this reaction of just the reduction of the ketone, okay, we've got lots of reagents that I could use to reduce. So here's a good test. I want some reagents. And I will list out 1, 2. Let's do, should we just stop there? Let's just stop there. 2 reagents that would do a reduction. And you cannot tell me sodium borohydride. That's already picked.
H2 in the middle.
H2 and a metal. That will do a reduction. What's your about?
It'll reduce everything. It'll hydrogen, all that.
Okay. And if we look at our starting material, what's the problem? There's a lot of pi bonds. That would reduce a lot of things. That's not what I want as an answer. So is that a good option as a reducing agent? No, but does it reduce? Yes. Right. So we could try and throw in the poisoned metal. And that poisoned metal reagent, H2, with our palladium and barium sulfate, or whatever you want to say, Lindlar's catalyst, does what kind of a reduction? Alkynes to alkenes. There's no alkynes, so while that is a reducing agent, I'm not going to count that in that list because I want it to reduce something that's up there. Come on, this one's easy. How about lithium aluminum hydride, or LAH? Okay. What's going to be the issue with that reducing agent?
Reduce the other ones.
That will reduce the carbonyl, but there's 2 carbonyls. Okay, it won't touch the alkene, so that's good. So no alkene reaction, but it will reduce both carbonyls. Okay, and since I only want one to be reduced, that doesn't work. So the reagent we could choose in this case would be sodium borohydride, okay, and that should reduce primarily just the ketone. Why does it not touch the ester? The ester is resonance stabilized, which minimizes its electrophilicity. Right? That in combination with sodium borohydride, what's the issue with sodium borohydride? It's not a very reactive hydride nucleophile. So I'm taking a weak electrophile and a weak nucleophile. Well, yeah, nothing's really going to happen. Okay? But lithium aluminum hydride can. Okay, so why? Why can lithium aluminum hydride react so much more violently, even with, say, a carboxylic acid, whereas sodium borohydride cannot? Okay, we started to address concepts on this in the last unit.
Is it just because the hydrogens are more nucleophilic?
Okay, why are the hydrogens more nucleophilic? I accept that as an answer.
Aluminum is not electronegative, so it doesn't stabilize the electrons on between the hydrogen and aluminum very well.
The hydrides in the lithium aluminum hydride are more nucleophilic. They are more negatively charged. Your explanation, aluminum is lower in electronegativity than boron. That's a good explanation. That makes the hydrides more negative. What else? Back to the more nucleophilic aspect. There's another big one.
Look at lithium.
As a hint. Aluminum is bigger in size, which means where are those hydrides held? further away, which then means the bonds are weaker, makes it more reactive. So two effects stack, making the hydrides more nucleophilic. Okay? Those are the big ones. The next difference is a hard one. And Tyler, since you started to mention it, I don't want you to talk anymore about it. See if somebody else can come up with it, as I box in the answer. The metals. The metals are different. Why are the metals being different going to change anything? Do either of those metals react? No. So that seems weird. Why are we talking about them? Okay. A lot of this is going to come down to the individual mechanism for how these reactions work. Okay, and actually, it's probably a little bit more like this. Lithium aluminum hydride is a good nucleophile, but in the presence of a carboxylic acid, what's the very first thing that's going to happen? You can come back in, Tyler, if you got it. What happened? Deprotonation. It's an acid-base reaction. Lithium aluminum hydride is a nucleophile. Right? It is such a strong hydride structure or presence that it can act as a base, which is why we have to do it in two steps. Okay? The second step is the acid source. Okay? Because if I added the acid right away, what happens? It kills the lithium aluminum hydride. Okay? So the lithium aluminum hydride will react with the acid to immediately form our carboxylate. What's the issue with forming a carboxylate in comparison to the carboxylic acid? What do you mean resonance? The carboxylate is resonance stabilized, which means what happened to the reactivity of our electrophile? It went down. Okay? Even with that first step, lithium aluminum hydride is so active as a nucleophile that it can still react. Well, how? Something has to mitigate that resonance effect. How could we minimize the ability of that oxygen to share electrons inward? That needs to stop. I would need a positive charge. Do I have a positive charge? The lithium and the aluminum. Lithium and the sodium are potentially floating around. What is the difference now between a lithium and sodium? Size. Sodium is bigger, which means what can it do to that negative charge?
Stabilize it better.
Is it going to stabilize it better? It's putting the positive charge further from the negative, which means weaker bond. Does the sodium stabilize that negative? No, which means resonance still happens. Sodium's not useful. Lithium, being smaller and more compact, can get its nucleus with all that positive charge a lot closer to the negative oxygen. Doing what to the negative oxygen? Stabilizing it, thereby no resonance. So we could look at a size effect. Lithium being smaller sets this up. What else could we look at? Electronegativity. What do we know about our electronegativity? It's get stronger as you go up, which means lithium is more electronegative than sodium.
Stabilize the negative charge better.
If I put a more electronegative element near that negative charge, that withdraws even more electron density away, stabilizing that negative even further. Okay? We can look at both the cation, okay, our counter ion, okay, the species that's a spectator that we would ignore. We can look at it for stabilizing our intermediates, and we can also move to looking at the nucleophilicity of our hydrides. And kind of just for giggles, You notice I wrote 2 and 3 for all of those. What was 1? Charge. We aren't really looking at a charge because it's all the same here. What's 4? I kind of accept size. It's molecular size, the size of the molecule, ultimately through resonance. How does a resonance stabilization come in? Okay. 5, an inductive effect, and 6. If we really got to go there, we're looking into hybridization is typically what we're classifying. Okay. It's those same rules that we've been looking at throughout the semester. Any questions about those? The big thing you need to know, lithium aluminum hydride will do it. Okay? It'll do the reduction. Okay? What would we expect here? We stepped it out, single addition at a time. There's our first hydride addition. Whatever all that other stuff is. Okay, what can happen? Our lithium can coordinate to the oxygen. And a second nucleophilic addition. We end up with our amine. Kind of, sort of? Please connect. Okay. Can we stop it? That's always a fun thing. If we start a reaction, typically we want to be able to control it. We want to be able to end it. Okay. Have we seen this pop up before? What type of reaction happened and now shown in red? A what? Reduction. Reduction means decreasing oxygen. Did we decrease oxygen bonds in red? No, we increased oxygen bonds in red, running right through the middle. Okay. So it's oxidation. We increased the bonds to oxygen. So you at least got on the right path that allowed us to evaluate and move forward. That's good. You looked at the other ones. It's okay. What if I wanted to stop at the aldehyde? What reagent could I use? Or let's switch this up because you didn't answer that fast enough. To go all the way to the carboxylic acid, what reagent do I use? Lithium aluminum hydride is a reducing agent, so we have to be careful here. We got the second person tripping up on this. I know, I'm making you double back. Permanganate would work. Okay, that's probably the less likely one to use. The issue with permanganate is it will oxidize alkenes as well. So we don't typically use permanganate because it's too strong of an oxidizing agent. What's the other oxidizing agent? Chromic acid. How could I go from the alcohol to just the aldehyde? PCC, or our pyridinium chlorochromate. We want to be able to stop at different stages along our track. Okay? The more control we have over the reaction, the better off we are. Okay? Which is what's happening in this next system. Okay? If I want to reduce the acid chloride, the very first step would be reducing it to the aldehyde. But then if I used lithium aluminum hydride or sodium borohydride, what would I get? I would end up with not the aldehyde, but the alcohol. What if I want the aldehyde? If I want the aldehyde, I need to stop there somehow. Lithium aluminum hydride is too stupidly strong a reducing agent, so we would likely expect that not to be a good one. The sodium borohydride is weaker, but even though it is weaker, what happens? Still reduces it all the way down. That's a bit challenging. How about the bottom one? Okay, we're starting with an ester. Is sodium borohydride going to work? No, we have to use lithium aluminum hydride. But if I use lithium aluminum hydride, what do I get? I go all the way down to the alcohol. Okay? So I need something to prevent further reductions.
I have a question. Could you then just go all the way and then just go back?
So that's not a bad idea. We could go all the way down to the alcohol and then use PCC to take us one step back. Fair enough, we could do that. Okay? And while that would work, ideally we do it in one step as opposed to two. But that's a good idea. Okay? Heard a lot of people mentioning issues with sterics. Okay? And sterics hasn't really played a role yet. And that's largely because our hydride is so stupidly reactive. But what happens if I attached, say, a massive carbon structure around the aluminum or the boron? Is that going to allow the boron to interact with the rest of the structure? No. Which then mitigates its ability to react. The reagents we end up using, okay, there's one name that really stands out that you should really spend some time memorizing. And that's got to be this bottom one, typically referred to as dibol or diisobutyl aluminum hydride. Okay, so you'll sometimes see it written as DIBALH. Which one's the active reducing agent? This form, red, or with blue? Blue. Blue shows the hydride. I need the hydride to be able to do the reduction. And then the top one, it's a lithium aluminum hydride, but instead of there being 4 hydrides, there's only 1, and the other 3, are filled with T-butoxides. What can you tell me about T-butoxide? It is massive. It is bulky. Okay. What can you tell me about diisobutyl? What can you tell me about isobutyl? Fair enough. I'm horrible with common names too. 1, 2, 3, 4. This is an isobutyl group. Shoot, that's sec-butyl. This is now an isobutyl. Remember, this piece here is referred to as iso, hence isopropanol. It is isobutyl because within the blue I have how many carbons? 4. Within the blue I have 4. 1, 2, 3, 4. Okay. What can you tell me about isobutyl? Sterically, pretty big. Okay. What ends up happening is in both these cases, that hydride source is now so large and sterically hindered that what happens to its ability to interact with the aldehyde? It loses it. It can't interact with the aldehyde. Okay? Which is kind of bizarre because in the bottom case, I'm reacting with an ester, which is what? More or less reactive than an aldehyde? Less reactive. I'm taking a species that shouldn't react to form an aldehyde. It's lower in energy, and I actually am able to make a higher in energy species because of this reagent. Okay, kind of a neat little species. Okay, both are sterically hindered, which is what prevents the aldehyde. Okay, we also run them both cold. Why would we run them both cold? We could see that. -75, -78, both cases. Why do we run them cold? It reduces the reactivity even further. Okay? If we heated them up, we run the potential for it overcoming the steric effects and potentially reducing it. Okay? So we run these very, very cold. Okay? I personally find these kind of a bit tricky because they don't match our ladder of reactivity. Okay? And we end up stopping our reductions partway through. Okay? So it's really going to be something that you just need to memorize. Okay? The one that I would highly encourage you to memorize more so than any of the others would be the dye ball. Dye ball is a super common reagent. It shows up in a lot of different places. Okay? What happens, couldn't I have done this with borohydride? Put the boron instead of aluminum in there. Yes, I could have done that. What happened if instead of using lithium or sodium, I used potassium? Was that going to change things? Potassium, did lithium and sodium have an effect on the reactivity? Yeah, they definitely did. Which then means if I switch to potassium, is that going to change how my hydride nucleophile will react? Yes, very likely. And what we end up finding is that there's a massive smattering of reducing agents, okay, of these aluminum hydride or borohydride reducing agents, okay, where they throw in a bunch of different ligands, the ligand being that extra piece. Okay. By adding in different pieces, I can change the reactivity of the hydride. Bottom line, if you see lithium or aluminum bound to hydrogen, what do you have? You have a hydride nucleophile. Okay, so if you can find that metal hydrogen bond, you've got your nucleophile. Okay, and it will get buried in a bunch of other different functional groups. Okay? So look for that metal hydrogen bond. That is your key signifier. Okay? Questions? Okay. Our organometallic reagents, these were our sources of R-. Okay? So in the reaction shown below, what happened? Substitution, how? What did the Grignard reagent do? Attacked the carbon? Attacked the carbon of our carbonyl, which then did what? First, we have to break the pi bond. So I know where you're going with that, Jennifer, but unfortunately, we have to go through and form our tetrahedral intermediate. I draw an extra carbon. 1, 2, 3, yeah. The electrons can come back down and kick out the chloride as a leaving group, and we would end up with that structure. What structure do I have? I have a ketone. Is this what I would expect to get as the product? Why does it keep reacting? There's still yes, the ketone still has an electrophilic carbon. Okay. Is it electrophilic enough to react with a Grignard reagent? Yes. That's what Unit 2 was all about. Yeah, it absolutely is. And what ends up happening? It consumes a second equivalent. I'd have 2 CH3s added to this. It would stall out at the oxyanion. At that point, what would I follow it up with? Step 2, H+, and I would end up with my alcohol. And I drew on that extra carbon again, didn't I? Okay. Grignard reagents are excessively reactive nucleophiles. They will react twice, just like our hydrides. Okay? Hydrides, if they're going to react twice, guess what the Grignards are going to do? React twice. Were there other carbon nucleophiles? So we had Grignards. There's 2 more that you are required to know. There's actually more than that, but 2 more big ones. Our copper lithium ones, also known as, what was that? our Gilman reagent. And I'm actually going to rewrite that a little bit lower. What's the last one? Fair enough, but no Wittigs. The Wittigs will only react with our carbonyls. We didn't spend a whole lot of time talking about this one because it was very similar to our Grignards. Our organolithium compounds, okay, it's the same kind of idea. Other ones, we have acetylides, we have our nitriles. Okay. We could even encounter enolates. Okay. All of these carbon nucleophiles we have to be aware of and thinking about. Okay. Why are we going to stick with the first three for the moment? What was special about those first three? Those were all our more reactive ones. The enolates tended to hover a little bit lower on reactivity. What was the special issue with our Gilmans? They weren't as reactive as our Grignards. Okay? They, in fact, reacted 1,4 addition. They preferred to react with the alkene of an alpha-beta unsaturated carbonyl instead of the carbonyl. Okay? So that would continue to react. Our mechanism, we just kind of walked through it, but we've got our standard mechanism, which your textbook gives you pretty nicely. I've not got a whole lot to add to that unless you've got a question, which I do not see. So predict your products here. Spence? Hopefully you're ending up with a tertiary alcohol in both cases. In the top case, we're adding 2 methyl groups. In the bottom case, we're adding 2 ethyl groups. Notice there's a whole bunch of junk running through the middle there on the second one. What is all this stuff? Okay. Probably the solvent. If you don't know, the first thing you should do is focus on where you find the most reactive atom. Okay. I see nitrogens and I see oxygens. Both of those could be reactive. Okay. Before I start panicking about that species, I want to look outside that. And I see, oh, I've got a magnesium up here. What does that magnesium do to this carbon? Makes it stupidly negative. Well, if that's stupidly negative, should I be worried about that red box? No. Don't stress about it. Focus on the negative carbon first. And if for some reason you still look at it and you're like, I don't know what's going on with that, most of your tests are multiple choice. What could you look for? An answer choice that has a bunch of those random little pieces jammed in it. If you don't see that answer choice, guess why it's there? To make you look at it and confuse and freak out and then stop working. Okay? Focus on where there's chemistry. Find the biggest chemistry first. Use your tests to help you through it and say, oh, that's a bunch of nonsense. Okay? Questions about what's up there? Okay? Try this one. Reactive enough to react a second time. Okay? That is a tricky thing. Okay? That is kind of a feature of our Gilman reagents. They only attack once. Okay? They will not react with our carbonyls. Okay? So our summary of interconversions. This keeps popping up, and I keep not realizing why I'm putting it in at different points. Okay? But it is an important thing to review. This sets us up with our most electrophilic and our least electrophilic of all of our acid derivatives and how to interconvert between them. The big things to remember, these are not equilibrium arrows for the most part. Most of these are one direction reaction arrows, starting at the top and moving downwards. Okay? It is not easy to go back the other direction. Sorry. This summarizes everything that our acid chlorides can do, okay, which is really all Chapter 20 was trying to get at. was kind of the big, fast reactions. Okay, our acid chlorides can go out to pretty much everything with virtually any nucleophile. So this is fun. Let's go ahead and do another quiz. So you guys should have seen this one already. I believe this is what I had Brian show you. I want you guys to go through and work this one out. Do I hear Esther? Does everybody agree, Esther? Nope. It's a carboxylate. Sodium ethoxide is a base. What's the functional group in your starting material? Carboxylic acid. What reaction do we get? Acid base. 4. This one was a little bit less irritating in my opinion. What do we end up with in 4? Just our primary amine. Michael? Gabriel. Oh, I get it. I was like, where'd you get Michael from? Yeah. 2. There's a couple answers I would accept in 2, though I think 1 is a better answer than the other. There was one suggestion that we have a reversible nucleophile, which becomes relevant if we say had an alpha-beta unsaturated carbonyl, which we do. So we could theoretically say that we would end up with the nucleophile attacking the beta position. Okay, and we've got our 1,4 addition. I would argue that's probably not the best answer because this oxygen does resonance in that direction to stabilize that carbonyl. Okay? If that carbonyl gets stabilized, what happens to the ability of the alkene to donate in? It's weakened, which then means I don't really have a very good 1,4 conjugate addition. Which means instead we should be focusing on, what's that? Attacking a carbonyl. Okay, doing a direct attack of a carbonyl. Which carbonyl do we attack? What's that? So I've got a vote to the alkene. Anybody else? Alkene or not alkene? Go for the non-alkene. Why'd you go for the alkene? Don't know. Okay. That alkene can do what? Resonance, which does what to the reactivity of the electrophile? It makes it less reactive through resonance stabilization, which would suggest that we should actually get our nucleophile attacking the other position. We'd end up with our amide. Oops, that should be an NH2. And then our alpha-beta unsaturated acid, carboxylate. Okay. 3. Anybody get the acyl bromide? What should you have gotten? No reaction. Why? Bromine is a good leaving group, okay, which would suggest what about the reversibility of this reaction? I would argue it's not even really reversible. It's unidirectional. Directional. Okay. The anhydride is lower on our scale than the acid, or than the acyl chloride or acyl bromide. We can't reverse. We can't go from the anhydride up to the acyl bromide. Reaction just dies. Nothing happens. And 5. Just our reduction. Oh, that actually worked out pretty nicely. Okay, we just reduce away our
So what does the acid
carbonyls.
What does the acid in number 5 do?
The acid is going to help reprotonate your nitrogen there.
Okay.
You won't end up with the alcohol. Oops, sorry, I didn't realize where that was. You do have an alcohol there. That one's an alcohol. Sorry, I thought it was an ester. It's too close. Okay, so it'll protonate that oxygen. It'll protonate the nitrogen too, but it'll also protonate the oxygen of the alcohol. The other one does not form an OH. That doesn't happen. Okay, because we have an amide there. Remember, when the amide reduces, it reduces down to the amine. Okay. If we're following along on the slides, there would be questions, but I decided not to do questions, decided to continue on. We talked about the Hell-Volhard-Zielinski reaction a little while ago. What chemistry is happening here? What does it look like happened? Overall, big picture, what changed? We did a substitution reaction. Substituted a hydrogen for a bromine. Typically, how do we supply bromine? How would bromine, what charge would you typically associate with bromine? Negative. Is it negative bromine here? Okay, no. We're getting bromine coming in Br2, which is an electrophile. It's positive. Okay? So we have a positive bromine coming in, which means what charge does our carbon need to be? That carbon needs to be negative. Okay? How could it become negative? What do I need to do? Resonance, tautomerization, remove that hydrogen so that I would then have the carbanion, right? That could then react. What do I need to help remove that hydrogen? Strong base. Am I given a base? Huh. Why not? What would the base do? It would deprotonate the carboxylic acid. It wouldn't deprotonate the carbon. Why? We want it to remove the red hydrogen. Instead, it would remove the purple hydrogen. The problem with that is that oxygen's better at stabilizing the negative charge. The purple hydrogen's the more acidic one. Okay, well, let's just say it did it anyway. Couldn't I then remove the red hydrogen? Why is the red hydrogen acidic? Stabilized via resonance with the carbonyl. If I have that red or that negatively charged oxygen, what can it do? Resonance with that carbonyl, which does what to the ability for the carbon to do resonance? Nullifies it. Acids do not have enolizable hydrogens for this reason, which means if I start with a carboxylic acid, there's no way this reaction is going to work. Huh. So that's why we don't add a base. Okay? But this still has to be what's going on. We're seeing all the standard pieces. We've got a positive bromine. That carbon must become negatively charged. Okay? I do have a negative bromine in there. What is the negative bromine going to do? Nothing. Super stable on its own. What else is added in there? What does PCl3 do? What does it do? Can you broaden that statement ever so slightly? What does it turn into chlorines? OH groups. Now there's no more hydrogen, which then means my red hydrogen is now enolizable. The acid chloride, because there's no resonance from the chloride into the acyl group, I can now do tautomerization on the other side, removing that hydrogen, reacting with the bromine to form, and now I'm kind of drawing in the middle of nowhere, this structure. Cool, I got the bromine attached. What did I want? The OH, how do I get the OH attached? Now I can add my water. Water's my good nucleophile. Kick it all back out, and I end up right back where I started with the carboxylic acid functional group. Okay. It's kind of a neat little reaction. That's why it gets that name, Hell, Volhard, and Zielinski. I think it's probably because it's three guys, which appear probably German or Polish. Okay. Lots of different things happening, all sorts of little steps, chunking along the way. Okay. I am over time, so I'll have to stop right there.